I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today, we are going to see about intrinsic semiconductors, and we are going to calculate or derive a very important derivation, that is the concentration of electrons in an intrinsic semiconductor. So this is the brief outline of the module, what we have discussed thus far and what we are going to discuss today. We are finished with the free electron theory, the Bloch theorem and chronic penny model, and in the last lecture we also have seen the classification of materials based on energy gap. And today we are going to discuss about intrinsic semiconductors and their carrier concentration. So how we are going to discuss about this topic, the electron concentration in intrinsic semiconductor. So first we need to understand what are intrinsic semiconductors. Then we are going to define the density of energy states. Then we define Fermi Dirac distribution and then derive the expression, because to derive the expression for electron concentration, it is very important to understand about the energy states and also the Fermi Dirac distribution. So we will first discuss these things and then go to derive the expression for electron concentration in intrinsic semiconductor. Now, if you see the classification of semiconductors, if I talk about semiconductor, a semiconductor is the one which is partially conducting, or the valence band and the conduction band are separated by a very small gap. That is what is the introduction of a semiconductor. Now, the broad classification of semiconductors, if you see, we have intrinsic semiconductor and extrinsic semiconductors. Intrinsic semiconductors are pure semiconductors. They are in the pure form. So, what do you understand by pure form? If I take a semiconductor germanium, all the atoms in the crystal germanium are germanium atoms only. There are no other atoms that are present in that. So that is why we call it as pure form. Intrinsic semiconductor means a pure form of semiconductor. For example, we are taking germanium and silicon, two very important semiconductors. Coming to extrinsic, whenever you add any other element to a semiconductor, to a pure semiconductor, you add something by doping. We call that process as doping. Doping means the process of adding an impurity to a semiconductor. Then it becomes an extrinsic semiconductor. In extrinsic, we have two types, N-type and P-type. But in today's class, we are going to discuss only about intrinsic. So when we come to extrinsic, I will explain both N-type and P-type also. So today's discussion, we are limiting to intrinsic semiconductors. Now, so what should you understand about an intrinsic semiconductor? I've kept the comparison between intrinsic and semiconductor so that the difference between the two will be readily available for you. We have seen an intrinsic semiconductor is always in the pure form, and in intrinsic semiconductor, the number of holes and the number of electrons are equal. We are going to discuss about this in the next few slides. Holes and electrons are equal. Then the Fermi level lies in between the valence band and the conduction band. So what is this Fermi level? Fermi level represents the energy level, which is the highest occupied. Okay, so this is in between the valence band and the conduction band, and the ratio of majority and minority carriers is unity. Majority and minority comes only when we are having, if the number of holes are more than electrons, then holes will become the majority carriers and electrons will become the minority. But in this case, because the number of holes is equal to the number of electrons, we say, so the ratio of majority and minority carriers will be unity. because it is the same. So the ratio, if you take it, is unity. So this is all about intrinsic semiconductor. So now if you take a pure silicon or germanium crystal, which we are saying it is an intrinsic semiconductor, each atom is surrounded by 4 identical atoms. Each atom possesses 4 valence electrons. So why 4 valence electrons? If you see silicon, it has 14 electrons. And how are these 14 electrons arranged? 2, 8 and 4. So 2 in the first orbit, 8 in the second orbit and 4 in the last orbit. So those electrons which are in the outermost orbit, we call them as valence electrons. So each atom possesses how many electrons? 4 valence electrons. These electrons, 4 valence electrons, are decided by the electronic configuration we see, which depends on the atomic number. Okay, so 2, 8 and 4. So 4 valence electrons, and they form covalent bonds with their 4 neighboring atoms. Why do they have to form bonds? Covalent bonds, all of you know, it is a covalent bond in which sharing of electrons takes place. So here, why they are forming? Because if you see, for an orbit, it has to be stable. It should contain 8 electrons in the outermost orbit, but it has only 4 electrons. With 4 electrons, it is unstable. So what is happening here is, it will form covalent bonds with the 4 neighboring atoms to attain closed shell configuration. This is what we call. What is closed shell configuration? We call it as the octet rule, which follows the octet rule, means 8 electrons in the outermost orbit. So to obtain that, it is going to form bonds with the neighboring atoms. Now at 0 Kelvin, there are no electrons in the conduction band. Why there are no electrons? All the electrons, the 4 electrons, they are forming bonds with the neighboring atoms and they are not free. So there are no free electrons. No free electrons means the conduction band is empty. So when the conduction band is empty means there is no electrical conduction. So the electrical conductivity is 0. So at 0 Kelvin, there is no electrical conductivity. Means it behaves like an insulator only. There is no electrical conduction at 0 Kelvin. This is what you have to understand first about an intrinsic semiconductor. Now we will see the diagrammatical representation of what we have discussed. So we are seeing the arrangement of atoms, silicon atoms in a crystal. So this is a lattice arrangement of silicon crystal. Okay, we are representing it in 2-dimensional representation of silicon crystal. There are more number of atoms. There are n number of atoms which we have seen. But we are representing only 9 to understand the bonds. So now if you are representing 9, each one is having 4 electrons. These are the valence electrons. Each atom, if you see, they have 4 electrons. All these are valence electrons of each atom. Okay. So for each silicon atom, there are 4 valence electrons. And these electrons are forming covalent bonds with the neighboring atom. Means this electron will form a pair with the neighboring silicon like this. And this electron with this. And there is one more silicon atom. If I am leaving it like this, means there are more atoms. So you have, if I take the central atom, it will be clear. So all the 4 electrons are forming bonds with the neighboring atom. So because of this, what is happening? All of them are fixed. None of the electrons are free. So how do we represent it in the form of a band diagram? So this is the band diagram here. So the valence band in which the valence electrons occupy all levels. All the valence electrons are here. And if you see the conduction band, it is vacant. Why the conduction band is vacant? If you see here, There are no free electrons. There are no free electrons. What happened to the electrons? They are forming bonds with their neighboring atoms and hence they are not free. So the conduction band is completely empty and the valence band is occupied. So the valence electrons are occupying all the levels in the valence band. So if you see here, we are representing it by EV, the energy level highest, and this is EC. This is the energy level of the lowest level in the conduction band. Now, as the temperature increases, what we have seen now is at 0 Kelvin. As the temperature increases, covalent bonds break. Electrons become free and they conduct electricity. So, when we have free electrons, there is conduction. So, as the temperature increases, it starts conducting. Now, if you see here, in free electron theory, they failed to establish a relationship between the two. How a temperature affects the conduction of electricity. So, what is happening here is, as covalent bonds are broken, electrons move to the conduction band, leaving holes in the valence band. Holes are nothing but deficiencies of electron. When we are talking about a hole here, hole is nothing but a deficiency of electron. Therefore, the number of electrons in the conduction band of a semiconductor is equal to the number of holes. So, if two electrons are moving to the conduction band, there are two holes in the valence band. So, it all depends upon the number of electrons that are shifting to the conduction band. Now, we see the figure here at temperature more than 0 Kelvin. So, if bonds are broken, so here we are seeing here one bond broken, one covalent bond which is broken because of thermal agitation or because of the increase in temperature, this bond is broken. So, when this bond is broken, there is one electron which is free. It is no more bonded with the neighboring electron. So, this electron is free. It is coming out. So, when the electron comes out, whatever gap we have, we will call it as a hole. The vacancy is nothing but a hole. So, first we are now starting the concept of electrons and holes in semiconductors. So, what are holes? Holes are nothing but vacancies. Vacancies from where the electron is removed. How is the electron removed? It is made free by supplying the energy. So, let us look at the band diagram, energy band diagram. So, we had at 0 Kelvin, all the electrons are in the valence band. Now, as the temperature increases, some of the bonds are broken. So, some electrons are made free and these electrons now go to the conduction band. So, you can see the electrons here. All these are electrons which are coming from the valence band. These have come from the valence band. So, when an electron is moving from the valence band to the conduction band, there arises vacancies in the valence band and these vacancies we are calling them as holes. So, these are holes and these are electrons. So, now if you see, always the number of holes in the valence band is equal to the number of electrons in the conduction band. Okay, so it all depends upon how many bonds are broken. So, how many electrons are made free. So, depending on that, we get the number of electrons and number of holes. Where are the holes now? They are in the valence band. The electrons are in the conduction band. In this case, in intrinsic semiconductor, we see that the number of holes is always equal to the number of electrons. If we are going to see both together, this diagram is very important for us to understand the derivation. So, what we try to understand here is, this is the valence band. This is the valence band. The lowest level represented by EVB and the highest is EV. All this represents the valence band. And here, this is the conduction band. This is the conduction band. The lowest is EC here and the topmost is ECT. We are representing it like that. And at 0 Kelvin, this is at 0 Kelvin, all the electrons are in the valence band and the conduction band is completely empty. And as the temperature increases, means at T greater than 0 Kelvin, some of the bonds are broken and from the valence band they move to the conduction band. So when electrons from the valence band move to the conduction band, there will arise holes or vacancies in the valence band. So there are electrons in the conduction band, there are holes in the valence band, and of course the number of electrons is equal to the number of holes. Now in order to derive the expression for the number of holes, what is the concentration of holes in the conduction band, we are going to derive. So for that we need to understand the density of states. So what is density of states? The density of states in a semiconductor equals to the number of states per unit energy per unit volume. Here if I am talking about the bands, this is the conduction band, this is the valence band. Now there are levels here, these are states we call. These how close they are spaced, that is the density of states. That is nothing but the number of states per unit energy per unit volume. So what we are going to assume here is the semiconductor can be modeled as an infinite quantum well in which the electrons with effective mass m star are free to move. So here again we are talking about effective mass m star. Till now whatever we are talking is about the mass of the electron. Even when we are talking about an electron, here we talk in terms of effective mass. Whenever our electron is moving in a periodic potential, we represent its mass by m star. There may be slight variation which we are representing it by m star. So the energy in the well is said to be 0. This we have already discussed. And this means the density of the states that is used to calculate the number of charge carriers per unit volume in any solid. So if I have to calculate the number of charge carriers, in this case we are calculating the number of electrons that are there in the conduction band. There are large number of states, energy states, and in each state there are electrons, and I will have to find the total number of electrons in the conduction band or the number of charge carriers per unit volume in any solid. Okay, so now the general expression or the expression we are going to use is ZC of ED, means the number of states in this energy range is given by ZC of E, is given by pi by 2, 8 me star by h square power 3 by 2 e power half d. So here I said ZC of E denotes the density of states, energy states. Me here is the effective mass of the electron. This is the effective mass. H is the Planck's constant. And E is the energy. T is the energy. So in order to get the density of states, we will directly use this formula pi by 2, 8 me star by h square power 3 by 2 e power half d. Now coming to the Fermi-Dirac statistics, how does this help us in calculating the density or the charge carrier concentration? It is a type of quantum statistics that applies to the physics of a system consisting of many identical particles. Our particles here are electrons and that obey the Pauli's exclusion principle. Actually, this Fermi-Dirac statistics is given for fermions that obey the Pauli's exclusion principle. So now Fermi-Dirac distribution function gives us the probability of occupation of electrons over a given energy state. If you are talking about a band, if I am talking only about a conduction band, okay, so these are the states, energy states. Now, what is the probability of occupancy of each state? In this, we need to know to calculate the density. So, what we are trying to understand, we will use Fermi-Dirac distribution function to know the probability of occupation of electrons over a given energy state. Now, this Fermi-Dirac statistics is a part of the statistical mechanics and it uses the quantum mechanics principles. It is based on the principles of quantum mechanics, and the expression we are going to use here, we will write it as C because we are using it for electrons in the conduction band. So, our Fc of E is given by 1 upon 1 plus exponential E minus Ef by kT. E is the energy we have already discussed, and Ef here denotes the Fermi level. Ef denotes the Fermi level. It is the highest occupied energy level. Then K here, K, or sometimes we may write it as Kb, is the Boltzmann constant. Kb is the Boltzmann constant. So we are going to use these two expressions to derive the expression for charge carrier concentration. Now, before I go into the derivation, let me give you a clear idea of why we are going to use these expressions. I will give you a simple practical example to understand this derivation very clearly. Suppose I want to count the number of students who are sitting in my class. Now I see the arrangement of tables. There are 4 columns and in each column there are 5 rows like this. So this is the arrangement, seating arrangement in the class. And generally if you see, we have 3 students sitting in each table. There are 3 students. Now I want to calculate or count the total number of students here sitting. So what is the first thing I do is, how many tables are there? So there are 4 columns and 5 rows. So 5 into 4, I have 20 tables. And how many students are sitting in each table? 3 students in each table. So how do I get the total number of students? 20 into 3. This is a very simple example to understand this derivation. What we are calling here the tables are the density of states. Whenever we are talking about density of states, you will have to relate it to the number of tables. And whenever I talk about the probability of occupancy, here we know that it is fixed. But sometimes there may be only 2 students sitting in one table. That time I'll have to consider only 30 tables into 2 students. So the probability of occupancy for the highest is 3. No, the lowest it can be 1 or 0 also. So depending upon the probability of occupancy, you will multiply and you will get the answer. Of course, if there are number of students sitting is different, then we will use. But here we are considering the same probability, no, for electrons. So hope if this concept is clear for you, to understand this derivation, it becomes very easy. So now what we are trying to find here is the number of free electrons per unit volume having energies between E and D in the conduction band is represented by NED. So NED is representing what? N here is standing for the number of electrons having energies in the range E and E plus D, and these electrons are in the conduction band. So we are talking about the electrons in the energy range E and E plus D in the conduction band, and we are representing it by N of E d. So this gives us the carrier electron concentration. Now, how do we get this? It is obtained by multiplying the density of states, which is represented by Zc, and Fermi-Dirac distribution function. So I told you, we need to multiply the number of tables with the number of students in each table. So what are the tables here? They are the density of the states, which is represented by Zc of E, and the Fermi-Dirac distribution, which talks about the probability of occupancy of electrons in each state. So therefore, N of ED, that is the carrier concentration, electron concentration in the conduction band, is given by the product of Zc and Fermi-Dirac distribution function. So Zc represents the number of energy states per unit volume, and Fc denotes the probability of occupancy. So by taking the product of these two, we are going to get the carrier concentration, that is the electron concentration in the conduction band in case of intrinsic semiconductor. So now where do we start? The total number of electrons in the conduction band per unit volume between the energies EC to ECT. Why we are talking about EC to ECT here is, when we see the lowest energy level in the conduction band, this is the conduction band. Now we are calculating the number of electrons in the conduction band. So this is the lower level EC and this is the highest level. So we are trying to get the electrons between the energies EC and ECT, and that is given by integration. So when you have to sum up everything, we do integration. No? So N is equal to integral of EC to ECT, N of E d. So first we will find within a small region d and then extend it by integrating between the limits EC to ECT. So by doing this, we get the total number of electrons that are there in the conduction band. So integral of EC to ECT, N of E d gives us N. Now this equation we can write it as, we can split and write it as EC to infinity N of E d plus integral infinity to ECT. Means we are splitting. This is infinity. Again we are starting from infinity. So continuous, these two. No? So I can write it as EC to infinity N of E d plus integral infinity to ECT N of E d. This expression, I am just splitting the limits. And now I can rewrite it as this. I will keep as it is EC to infinity N of E d, but this I will interchange the limits. I will write now from ECT to infinity, then there will be a minus sign. This will reverse. So I am writing it from ECT to infinity N of E d. Why I am doing this here is, if I am talking about the number of electrons in the region ECT to infinity. So the highest band is ECT, and above this we have till infinity. We are talking, suppose there are energy bands. Are there any electrons in this region above ECT till infinity? Any electrons here? No. So this term will vanish. So the second term vanishes because there are no electrons above ECT. So what we are left now with is only N is equal to integral EC to infinity N of E d. Means I am taking directly from here to here. Of course, they are not there. So only these will be counted. Now I am going to substitute for N of E. N of E, how we are getting? By multiplying the density of states and the probability distribution function. So I am writing in place of any E, I am writing Zc d into Fce. Now what is Fce? It's a Fermi-Dirac distribution function which talks about the probability of occupancy of electrons in each energy state. So we are going to use the expression and we will simplify it and substitute. So Fc of E is 1 upon 1 plus e power E minus Ef by E kBt. So here E is much greater than Ef. Ef, I told you, is talking about the highest occupied energy level, but the Ne in this case is much higher than Ef. So what we are going to see here is E minus Ef will be very high. If you are talking about E very high, so this term will be very greater than 1. So simply we can neglect this one. If this value is very high, we can simply neglect the value of 1 and write it as 1 upon e power E minus Ef by kBt, or neglecting that 1. No, considering E to be very large. Now, if I take this term to the numerator, what will happen? I have here f of CEE is equal to 1 upon e power E minus Ef by kBt. I take this term to the numerator, all the signs will change. So this minus Ef will become plus Ef, and this plus E will become minus E upon kBt. This is how you write Fc of E is equal to e power Ef minus E by kBt. This is the expression we are going to use. Now we have already seen that the density of states is given by pi by 2, 8 me star by h square power 3 by 2 e power half into d. So what this is representing is the density of states in the conduction band. And again, E is greater than EC. Why E is greater than EC? EC is the minimum state. When I have shown you the conduction band, there are different states. This is EC and this is ECT. So this is the lowest level. Any other energy is above EC. So EC is the minimum energy state. So we are going to modify this equation 8 by writing E minus EC in place of E. Means we are accommodating all within this range. So instead of writing E, we are writing E minus EC. So now we are going to put equation 7, that is the Fermi Dirac distribution function, and also the density of states in equation 5. What is our equation 5 for N? N is equal to Zc of E into D. So here when you substitute, you have integral EC to infinity pi by 2 8 me by h square power 3 by 2 E minus EC power half, representing the density of states, multiplied by the probability function. What we have got here? Fermi Dirac distribution function. So when you are taking out all the terms which are constant outside the integral, pi is a constant, 2, 8, me h square power 3 by 2. All this is a constant, so we are putting it outside the integral. And integral EC to infinity E minus EC power half E power EF minus E by kBt. What we have done here is only simply putting the constants outside the integral and writing the other terms as it is. Now we'll do a small substitution. Let epsilon be equal to E minus EC. So we are taking the term E minus EC to be equal to epsilon. Now, d epsilon will be equal to d because EC is constant if you are taking the derivative. D epsilon will be equal to d because EC is a constant. Now, how will the limits change? We have seen the limits now between, what are the limits here? We have taken from EC to infinity. How these limits are going to change? Initially, it is from EC to infinity. Now, when I substitute this condition, epsilon is equal to E minus EC. So, in place of EC, I will put EC first. So epsilon is equal to EC minus EC. That will give us 0. So the lower limit will be 0. And for the upper limit, in place of E, I will put infinity minus EC. So this is infinity. So what will be the limits now for epsilon? It will be from 0 to infinity. So epsilon will take the values from 0 to infinity. And now I am writing the same expression with the limits from 0 to infinity. All this is a constant. And we have, for E minus EC, we have substituted epsilon. So we get epsilon power half into E power EF minus E. What we had here? E power EF minus E by kBt. Now in place of E, what I can put here? This implies E is equal to epsilon plus EC. So from this expression, epsilon is equal to E minus EC. I can write for E, taking minus EC to the other side, I get plus EC. So E is equal to epsilon plus EC. So E power EF minus epsilon plus EC upon kBt. I can take out the constants outside here. EF is a constant, EC is a constant. So I can write it as EF minus EC by kBt into E power minus epsilon by kBt. Are you able to understand? With the substitution we have taken, E minus EC is equal to epsilon. I am going to substitute here in the case of Dirac function. So E power EF minus E by kBt. For E I have substituted minus epsilon plus EC. So EC is a constant, EF is a constant. So I have put it separately. EF minus EC by kBt into E power minus epsilon by kBt. Now this also I can bring it outside the integral. So if I can bring it here outside the integral, I have all this to be constant. Integral epsilon is equal to 0 to infinity. Epsilon power half E power minus epsilon. Only this term remains. Minus epsilon by kBt d. Now we are going to use again one more result, that is integral epsilon is equal to 0 to infinity epsilon power half E power minus epsilon by kBt d is given by root pi by 2 kBt power 3 by 2. So for this we are going to substitute this value, root pi by 2 kBt power 3 by 2. So on substitution 12 in 11 means in case of the integral, we are going to substitute root pi by 2 kBt power 3 by 2. So all this is what we had as a constant. And now we have substituted after integrating, we are getting root pi by 2 kBt power 3 by 2. Now I will simplify these terms. I will combine, rearrange and write. What we have here is pi and there is pi power half. So pi into pi power half. Pi into pi power half is giving us pi power 3 by 2. So here I have root pi into pi as pi power 3 by 2 and kBt power 3 by 2. We also have kBt power 3 by 2, whole power 3 by 2. Here we have 8 me by h square power 3 by 2. 8 me, this is effective mass by h square power 3 by 2. All these terms which have power 3 by 2, we can combine them and write it as 8 pi me star kBt by h square power 3 by 2. I hope you are able to understand how we are combining. Pi into root pi is pi power 3 by 2, kBt power 3 by 2 we have. So 8 me by h square power 3 by 2 is there. So everything we are combining and writing it as 8 pi me star kbt by h square power 3 by 2, and we are left only with this. So we are writing e power ef minus ec by kbt in the denominator. In the denominator, we have 2 here and 2 here. So 2 into 2 is giving us 4. So what is the expression we have now? N is equal to 1 by 4. 8 pi me kbt by h square power 3 by 2 e power ef minus ec by kbt. Now we are going to do one more simplification here. What we have here is 8 power 3 by 2, and here in the denominator we have 4. So how I am going to substitute for 8 power 3 by 2? So this 8 I can write it as 2 into 4 power 3 by 2, or 2 power 3 by 2 into 4 power 3 by 2. So 2 power 3 by 2 into 4, I can write it as 2 square power 3 by 2. So this gives us 2 power 3 by 2 into 2 cube. This 2 and this 2 will get cancelled. So 2 power 3 by 2 into 2 cube is nothing but 2 power 3 by 2 into 8. So this 8, I am bringing it outside, and this 2 power 3 by 2 is inside. So I have 2 power 3 by 2 and this is 8. That is how we are getting this 8 here. So just by doing simplifying 8 power 3 by 2, you are able to write it as 8 by 4, 2 pi me star kbt by h square power 3 by 2, and this term remains as it is. So you can simplify this now. 8 by 4 gives us 2. 2 pi me kbt by h square power 3 by 2. E power, we are simply writing it as EC minus EF. Why? Because when we are talking about EC and EF lies below EC. No? Therefore, we are always trying to write the higher energy value minus the lower energy value. So the same expression what we are trying to do here, take out a minus common so that it will become minus EC minus EF by kBT. It is only to represent it in that higher minus lower energy. So what we have here is 2 pi me kBT h square. All these are constants. So what we are going to do is, for all these constants, we are going to represent it by NC. Capital NC is a constant which is 2 into 2 pi me kBT by h square power 3 by 2. So for all this, if I substitute NC, how do I write the expression for N? So N will be equal to NC. This is NC into e power minus EC minus EF by kBT. So this is the final expression we are going to get. So N is equal to NC into e power minus EC minus EF upon kBT. This gives us the concentration of electrons in the conduction band in an intrinsic semiconductor. We can also write the same expression without writing NC, and wherever we are doing numericals, we will be using this expression. N is equal to 2 pi me kBT. Me star here, again I told you, it represents the effective mass of the electron when we are considering the periodic potential. So 2 pi me kBT by h square power 3 by 2 exponential EF minus EC by KT. So you can also write it as exponential minus of EC minus EF by KT or KBT. Both mean the same. I can write it as KB also. Even if I write as K, it is the Boltzmann constant, or KB. Okay. And here what we are having here is N is equal to 2 into 2 pi me, of course, star by h square power 3 by 2. So this is the expression we are going to use to calculate the concentration of electrons in the conduction band. So if you see the derivation at a stretch, you may find it is very clumsy and it is difficult to understand. But if you follow definite steps, I will give you some steps how to understand and do the derivation, then it becomes very easy for you. So the first thing what you have to do is you will have to define what is Ne, the concentration of electrons in the conduction band. That can be obtained by multiplying the density of states with the probability. Fermi Dirac function. This gives the probability. So the first step you need to know is this is obtained by multiplying the density of states with the Fermi Dirac function. This is the first stage. Now if you have to apply from DE, if you have to extend it for the entire band, what we are going to do in the second step is we are going to integrate this between the limits EC to infinity. So this limits also you need to understand how we are splitting, and we are writing it from EC to infinity. So again this gives us Z of E D into FC of E. So first we have taken for a small region DE, and then we have extended to the whole by integrating between EC, the limits EC to infinity. And in the third step what we are doing, we are taking the expressions what we have for the density of states, pi by 2 into 8 me pi h square power 3 by 2 into e power half. So this is what you need to remember for the density of states, because you have to take the product. And the fourth step, you are also considering the Fermi Dirac function, which gives us the probability. So FC of E is given by 1 upon 1 plus e power E minus EF by kBT. And then you are going to simplify this, and you are getting e power, after simplification you are using e minus EF minus E, e power EF minus E by kBT. By neglecting 1, because the value of E is very large, and taking it to the numerator, the signs will change. So EF minus E by kBT. So once you are getting these two, you are substituting here in the limits EC to infinity. Now you will substitute, rearrange, take all the constant terms outside, and also you will have to use one more relation, that is integral 0 to infinity epsilon power half into e power minus epsilon by kBT gives us what? Root pi by 2 kBT power 3 by 2. You will have to use this relation. Of course, what is epsilon here? Epsilon is equal to E minus EC. So this puts the limits, this changes the limits for epsilon from 0 to infinity. On substituting, you get this. So you have epsilon power half e power minus epsilon by kBT integral value this. So the first step, second, third, if you follow these steps very carefully, then it becomes very easy to substitute, understand, and the final result what you get here, that is the concentration of electrons, is given by 2 into 2 pi me kBT by h square power 3 by 2 into e power EF minus E by kBT. So this is the expression we are going to use to find the concentration of electrons in the conduction band of an intrinsic semiconductor. And you need to practice, understand the terms, and then apply them. Thank you. See you again in the next class.
Like, share and subscribe. Hit the bell icon for more updates.